So these things are just staggeringly luminous. They have to be give us so many gamma rays, even when that's such enormous distances. So, Brian, we had a whole bunch of models we talked about, from colliding comets through to black holes. Which of these models best fits what we're seeing here?
Well, just because of the sheer energy required to get, that many gamma rays out in such a short period of time, the obvious thing is the formation of a black hole, because you get to take all that energy, all that mass, more than a solar mass of stuff, and take it down to that tiny little radius. And so that is a way that we can imagine to get that amount of energy out of such out of an object. So it was, but we don't know that for sure.
It was a very exciting time. Every time I was at the telescope, I would invariably get yet another phone call, yet another gamma ray burst to be located. Please point it here. And probably every observer in the world probably got the same sort of phone calls. I dread to think what the phone bills run up by these people was. But so over the next year or two, a number of these gamma ray bursts are pinned down, and they seem to be picking up a pattern. They were all at these sort of distances, several billion light years away, and therefore all incredibly luminous. But then there was a surprise, which you were quite heavily involved in, Brian.
Yeah, so I remember it was April 1998, and one of these Beppo-Sachs gamma ray bursts went off, and we were able to point our telescopes at the particular part of sky up at Mount Stromlo. Now, it was the middle of the night, so we didn't really worry about looking at the data until the morning. I'm sorry, I was a little lazy. I had a small child. That turned out to be a mistake, because as the object came up and was observed around the rest of the world, it was immediately identified as an object had appeared in a galaxy. But this galaxy, this is an image taken from the ground, not with the Hubble Space Telescope, and this galaxy is really nearby at a redshift well less than 0.01. So this was a funny object that, wasn't that bright in gamma rays, but was really, really nearby.
So presumably it must be much less luminous than the other ones we talked about.
Yeah, so the question really was, are we sure that this is a gamma ray burst? Because there was a complication. And this complication is that when we turned the X-ray satellite around to look at this area, there were actually two different places that there was X-ray light that had come. Not very bright X-ray light. There was this one, and that's contained that galaxy. And there was this one. So this is the circle where you could isolate the X-rays.
Yeah.
And I should say this big circle is where we thought the gamma rays came from.
So they knew the gamma rays were somewhere here. As you can see, there's a lot of stars in that region. But when they took the X-ray picture, there was X-ray source somewhere here and X-ray source over there somewhere. And so it could have been that there was actually some much fainter thing in here.
Right.
The supernova was just a coincidence.
That's right. And to make life even more complicated and interesting, it turns out the other way you can measure places on the sky is by timing. And so there was a satellite, a bunch of satellites out that would see the little pulse of gamma rays. And by timing them, they get this circle where things can be in the sky. And that circle went right through both X-ray sources. So there was a real conundrum in the community. People like me, who study supernovae, had observed this supernovae, and we realized it was unlike any object we had ever seen before.
So what was odd about it?
Well, it was expanding at 25% of the speed of light. So it was on order of 80,000 kilometers per second was how fast this supernova.
That's a lot faster than most supernovae.
It's like a factor of 3 faster than any supernova I had ever seen. And so we had also discovered it right after explosion. And so when someone says, go look in this direction, and you look in that direction, and you see something that no one has ever seen before right after it exploded, and you tell me it's a coincidence, well, I said, and my friends, no way. But the gamma ray burst community was so convinced that these things must be at large distances that they really felt that this might just not be real.
And you do get coincidences like this. The number of times that some totally weird, highly improbable coincidence has come up and people have read great things into it and then it turned out, oh, it's just a fluke.
Yeah, so anyway, what we had to do was to keep on looking. The problem is that most of the gamma ray bursts are so far away that you can't possibly see their supernovae because the supernovae are just too faint. And supernovae are interesting because we think supernovae are where you might form black holes sometimes. As the star collapses, if it's a really big star, the center of the star will collapse down potentially to a black hole.
Yep, so if we really could prove that these gamma ray bursts were associated with supernovae, then that's a lot of evidence for the black hole model. The trouble is this gamma ray burst was a very unusual one, much less luminous than most, so maybe we got yet another type of gamma ray burst here.
Yeah. So, like anything, it's important to wait and see what happens. And we had to wait quite a long time till we had our next opportunity to really see if there was a black hole being formed in a supernova from one of these gamma ray bursts. And that opportunity came in 2003. Now, in 2003, we were still busily looking at these exploding stars that would happen every month or so.
There were more satellites now giving us...
Yes,
accurate
there was a new
positions.
one called Hetty 2. Remember, Hetty 1 was the one that failed. Hetty 2 was the new one. And so on the 29th of March 2003, one of my students got a phone call in the middle of the night. Now, it was cloudy up at Siding Spring, which is the main observatory up near Coonabarabran. But he said, what the heck, I'll point the telescope up towards where this thing is. And this is what he saw. He didn't see any stars, but he saw one thing beaming through the clouds. And he realized it must be very bright.
To see it through the clouds with a
Yeah.
1 meter telescope, this must be incredibly luminous.
It was a very, very bright object. It was, again, almost bright enough to be seen with a very small amateur telescope. And so we pinpointed it, and that allowed other people in clearer sights to go out and look at it. And it turned out to be at a very low redshift, redshift 0.16. But the difference was that this one was one of the brightest gamma ray bursts ever seen. So it was as the right luminosity. It was a normal gamma ray burst that just happened to happen in the nearby universe.
Oh, so that's much better now. We've got something which has the right gamma ray luminosity.
Yep.
It's very nearby, but therefore has huge gamma ray fluxes observed by us. So that must have kept the gamma ray people happy. They must have thought, okay, this really is a normal gamma ray burst that just happened to go off very nearby.
That's right. And so then as the gamma ray burst faded, we all waited in anticipation, looking with the biggest telescopes at the spot to see if a supernova appeared. And voila, 12 days later, a supernova appeared that looked almost identical to the one of 1998.
So it had the same very high velocities.
Same very high velocities. It really looked, I mean, it was like almost an identical twin in all ways and respects. So it does seem that these gamma ray bursts are formed when a black hole is made in certain types of supernovae. But obviously, although the supernovae were almost identical, this gamma ray burst was thousands of times brighter than the nearby one associated with the 1998 object. So, as during this time, when we were out looking at gamma ray burst after gamma ray burst, we had a lot of opportunities to look at all sorts of objects. And as we got more and more objects, we of course got the record holders, the ones that was the most distant object yet seen. And in this process, we actually had a few surprises.
So here's another record holder.
So this object, gamma ray burst 990123, so that means it occurred on the 23rd of January 1999. And this object was caught by a specialized robotic telescope that could take the signal from space of where the gamma rays were and slew there within a few seconds.
So cutting out the excited phone calls in the middle of the night.
Exactly. And so when it got there, it saw something that got very bright. This was just a teeny weeny little telescope, and this object reached about 1/8 magnitude. So that's something you can easily see in a pair of binoculars. This was the brightest gamma ray burst that had ever been seen to that date.
Was it another nearby one?
Well, you might think so, but it turned out, when we looked at it in detail, it was in a tiny galaxy halfway across the edge of the universe at a redshift of 1.6. That's 9.4 billion years ago. So this thing was amazingly luminous. It was as bright as, as a very nearby star, and yet it was 2/3 of the way to the edge of the universe, to the time of the Big Bang.
Okay, so let's actually work out what its luminosity is. So we know the fluence, considerably higher than last time. We know the distance, also higher than last time. So the energy, once again, is 4 pi d squared times the fluence, which comes out at an absolutely whopping 4.9 by 10 to the 47 joules. So that's way more than last time because it's both further and at a higher flux. That's a staggering amount of energy. To put that in comparison, how much matter would you have to convert to energy to make this? Well, the energy you get from converting matter is given by E equals mc squared. So to work out the mass, you simply take the energy and divide by c squared, the speed of light squared. So this corresponds to a mass of about 5.4 by 10 to the 30 kilograms, which is 2.7 times the mass of the Sun. So that's how much matter you'd have to convert to energy to power this